So speaking of the silicon we just talked about that has a similar property to carbon in terms of sp3 hybridization, and also forms a tetrahedron, we can start looking at the silicate structures that use a similar tetrahedron to build their structures. So silicate is basically an arrangement of silicon and oxygen. So SiO4. So one silicon at the middle is the cation, and then four oxygens in the tetrahedral arrangement, and therefore we kind of count the charge as 4 minus. So this is the silicate base SiO4 structure, and silicates are basically just taking this arrangement and building it into more and more complicated structures. So we can have something like this where the one of the oxygens is shared between two. We can have this where it's a little bit more complicated and forms almost like a ring, where multiple oxygens are shared in this structure. And same thing here, where we form a larger ring, and then here where it forms kind of a chain, that again building off this tetrahedron. So when we have these types of effects, we refer to the oxygen in two ways. If we have something like this, where the oxygen is bonded to two silicons, right? So basically that oxygen is shared. We call that oxygen a bridging oxygen. And the other case where we just have a sort of a dangling oxygen there, and it's only bonded to one silicon. So this one here, this one is the opposite. So we call it non-bridging. So those are, in silicates, those are the two types of oxygens that we think of. And so we put together these more and more complex silicate structures, and we look at the number of bridging and the number of non-bridging oxygens as a way to indicate structure. And so whether you have non-bridging or bridged oxygen also changes something else. It changes the oxygen to silicon ratio. That's a kind of easier test of that. So we're going to have, in this case, we're looking at a very complex three-dimensional structure like quartz, or this one's called cristobalite, but basically what's happening here is that all of the oxygens in these structures, so all of these red and all of these blue over here, are bridged. So everything is bridged. And so in that case, the amount of oxygen is relatively low compared to the silicon. So 2 is our lowest. So, and that's SiO2, right? So 2 over 1, that gives us 2. So these types of structures, these three-dimensional structures, have this oxygen to silicon ratio of 2, and that means that the oxygen all of them are bridged in these structures. So this oxygen to silicon ratio we can actually use to predict the silicate structure. So I've got another table here from that same textbook. This one is 3:4, and it gives the ratio between, or the relationship between the ratio and the type of structure. So the one we just saw up here, this three-dimensional network, so cristobalite, tritomite, cristobalite, all of these polymorphs of silica, SiO2, have a ratio of 2, and that means that they have all bridged and 0 non-bridged oxygens. So that's what we have. And when you look at these diagrams, just keep in mind that this shape is basically a two-dimensional way of representing that SiO4 tetrahedron. So anytime you see this, think that there's a silicon in the middle, and then each point on here is one oxygen. So that's what we have in terms of the tetrahedron here. So if you're looking at any of these shapes. All right, so now let's go ahead and look at what happens if the ratio is larger. So in the next category, if we have something from 2.5 to 3, you can tell that we're going to have more and more non-bridged oxygens. And sure enough, that's what we have in these cases. So for 2.5, it gives us 1 out of the 4. And then down here at 3, we have half that are non-bridging. So these shapes, or the structure that results, are different shapes. So for 2.5, when we have one non-bridged, it gives us a planar structure. So these are, or sheets, infinite sheets. So these are just planes, and then the planes are held together. And then for the higher numbers, 2.7 and 3, these give us chain-like structures. So either a double chain for 2.75 or a single chain for 3. So this is, you can kind of see that we're going from a 3-dimensional structure to a more 2-dimensional structure to a more 1-dimensional structure as we add more and more non-bridging oxygens into these silicates. So some examples of these sheets, first of all. So you're probably familiar with something like mica or talc or clay structures where you have that like flaky sheet-like structure, right? You might have seen a mineral like this where you can peel off layers, right? So each one of those layers is a layer of the silicate structure, and then there's things in between holding them together. So that's what we have in all of these cases. All right, so the 2.75 to 3, these are the chain structures. And one kind of example that you're probably going to be familiar with in this is asbestos. So asbestos is a double chain structure. And because of this kind of chain-like linear structure, the silicate that forms is very linear and chain-like and forms into fibers. So you can see this is natural asbestos where it forms into this fiber-like structure, and therefore it makes it good for building insulation material because we can build this fiber material that has a lot of empty space and doesn't conduct thermal energy. However, that fiber structure can also get stuck in your lungs and give you cancer. So there's a little bit of both on that structure. All right, and so let's go to the other extreme now. So now the highest amount that you can have of oxygen to silicon is just one of those SiO4 tetrahedrons. So that would be 4, right? So this is the absolute maximum you're going to find. And this means that none of the oxygens are now bridged and all of them are non-bridged. So you basically just have this isolated SiO4 tetrahedron. So if you're wondering how this type of structure happens, it happens because you have these tetrahedron and then you have isolated free ions in a structure that balance that charge. So we have a -4 charge here, so we have positive cations to balance out these types of charge. And so an example of this type of structure is the olivine. This is the mineral olivine, and then this is its structure, where we have these isolated tetrahedrons balanced by all these free electrons in this structure. All right, so let's take a look at one of these materials and see if we can predict the amount, or sorry, we can predict the structure based on that oxygen to silicon ratio. So this is a mineral named Lizardite. So I thought it was a funny name, so I put it on here as an example. This is the stoichiometry compound Lizardite. So taking this information, see if you can use that table 3.4, and I'll put this in. This is also in the same PDF that you had containing table 3.3 also has 3.4, so you can use that as well and see if you can predict the structure based on what you see here with the stoichiometry and compound information. So do that, pause the video, and we'll come back and take a look at this. All right, so to be able to predict the structure of Lizardite, which I've rewritten here, again, we need to know the oxygen to silicon ratio. So let's go ahead and calculate that. All right, so if I count up all the oxygens, they're OH4, so that means I have 4 oxygen here, 9 here, so 9, and then I have silicon 2. Well, if I do this, I just show that I got 4.5, right? So when talking about the S21O4 tetrahedron, I told you that the oxygen to silicon ratio of 4 was the absolute highest we can have, right? So what's the deal here? So it turns out that we can have, in the overall compound, right, we could actually have more oxygen than what we see in this, but the oxygen is not part of this tetrahedron, right? And as it turns out, they've actually already drawn it or organized it for us in such a way to show that these OH groups are not part of this SiO4 network. So the OH groups are separate, right? That's a chemical group, hydroxyl group that's kind of separate. And so they've already actually done that. And so we know that these don't count. It produces too high of a number. And so really all we're concerned about is the SiO here. And so that's where these are the ones that are networked together as part of this tetrahedron. And so instead, so this is not correct. So instead, we should only count these. And so our O to silicon ratio is 5/2. That gives us 2.5, right? And so if we go to our table there, we see that according to our table, going back, that gave us the infinite sheets, or you might call it the planar structure. So that's the kind of structure you would expect with a number of 2.5 relating back to, that's from table 3.4. So again, this was an example I wanted to show you where they've actually organized it for us such that this part, those oxygens don't contribute. When we talked about the oxygen to silicon ratio, we're just talking about this form. So most of the ways that you're going to see these compounds written, they've actually separated it out for you to make it more convenient to do that. So that's how we can predict silicate structures.